Yes, thank you for the introduction, and thanks to everyone for being here. So the goal of this work, and to a lesser extent this talk, is to clarify the implications of different definitions of semi-supervised sample complexity. Wait, why is this not as a presentation? Control what? Control level. Yes. There you go. And semi-supervised in this case means that we assume that our algorithm in the supervised learning problem has access to unlabeled data in addition to labeled data. Now, just as a quick reminder of why we might think that this could help, let's say we have this classification problem. We want to learn a linear separator. Given this labeled data, we would maybe learn this one. If we had access to additional unlabeled data, which is cheaper to acquire, we would see that a separator with a better margin would be this one, and in the end, we would have learned a better classifier. So if you're already thinking of checking out the too long didn't listen of this talk, is I will define what rate improvements through unlabeled data means. I will convince you that this definition differs from idealistic definitions in a significant way, and then there's some clickbait at the end. So our setting is the typical supervised learning setting. We have a feature space X, binary label space Y. Assume there's some underlying distribution. We're given a hypothesis set of classifiers, and we measure the performance of a classifier in F by the 0-1 loss. Now, if we have some learning algorithm A that maps to the set of our classifiers, note that we're not assuming proper learning here, so it might return something that's not in the hypothesis class. Then we measure the performance of this classifier using the expected excess risk. So we evaluate how much worse the classifier returned by this algorithm is than the best in the hypothesis class H, in expectation over all possible samples. Now, PAC sample complexity bounds would be another way to look at this, but then we introduce additional parameters and it becomes more complicated, which is why we opt for this view. Now we're looking at the theoretical limits of the approach, so we want to take the worst case distribution and also the best possible algorithm. So we're not looking at any specific algorithm, and we can view this minimax expected excess risk as a function of L, and then investigate the convergence rate of this minimax risk as we add labeled samples. Now, in the supervised setting, this convergence rate is characterized by the VC dimension, as we know. So if H has finite VC dimension, we have convergence rate 1 over square root of L. If we add realizability assumptions, 1 over L, and if the VC dimension is infinite, then we have no convergence. Now, let me define what we mean by rate improvements. Rate improvements mean that if we plug in semi-supervised algorithms in this minimax expected excess risk definition, we get faster rates than if we plug in supervised algorithms. So if you don't want to parse this whole, all of these contours, just think faster rates. Or the semi-supervised rate is dominated asymptotically by the supervised rate. So in general, the way it's stated here, the answer to this question, sadly, is no. The reason for this is that in the supervised case, we already have tight lower bounds on some unfortunate shattered distributions. And the bad performance of the supervised algorithm on these distributions does not depend on the fact that the algorithm does not depend on whether or not the algorithm knows the marginal. So if we plug in a semi-supervised algorithm, we still get the same result. So we could give up, but naturally we won't, because we suspect there's still some room for improvement through semi-supervision. So let's add distributional assumptions to the minimax rates. So we let our supervised and semi-supervised algorithms compete on a restricted set of distributions. And then how do we define a semi-supervised rate? We introduce some kind of unlabeled budget function U. So given a labeled sample size L, say 10, this budget function U tells us that in this setting we would assume to have, say, 100 unlabeled examples, and so on. And then the semi-supervised minimax rate with this unlabeled budget is the best possible algorithm, the worst possible distribution in our assumption set P, and we assume that our algorithm receives a labeled sample of size L and unlabeled samples of size U of L from the marginal distribution of the data. Now, Another way to define semi-supervision would be to assume that the semi-supervised algorithm has access to the marginal distribution of the data. So this does not seem too unreasonable because, in fact, we could estimate the marginal from unlabeled data. So why introduce this extra parameter u? So I will now convince you why this is like an important distinction. So if we instead chose to let our semi-supervised algorithm depend on the marginal of the distribution as well as a labeled sample, then previous results show that we can have problems, so hypothesis class plus assumptions that are unlearnable in the supervised setting, but if we have access to the marginal distribution, suddenly we become learnable. And this is quite a significant gap that makes it seem like semi-supervision is extremely powerful. However, we show that using any kind of unlabeled budget, this result cannot be replicated. So it's not possible to go from unlearnable in the supervised setting to learnable in the semi-supervised setting using any kind of limited unlabeled data. The conclusion is, if you want to show that you have better rates through semi-supervision in an indisputable way, use our definition instead of using idealistic assumptions. And now for the party trick. One observation to keep in mind when working with unlabeled data is that it can happen that even though you make assumptions that lead to the marginal distribution completely determining what the correct labeling function is, you may still not get a change in semi-supervised rates with budgeted unlabeled data. You can see this in a very simple example. Let's say I assume the feature space contains only 2 points, x1 and x2. We assume that these points have opposite optimal labels. One should be labeled with 1, one should be labeled with 0. Now, in addition, let's say we assume that the point that has higher probability mass in the marginal should be the one that's labeled 1. So as soon as you know the marginal distribution, you know which one has higher probability mass, you know the optimal labeling. And since unlabeled data can be used to estimate which point has higher probability mass, it seems like unlabeled data should be quite helpful in getting better rates. However, among other examples in our paper, we show that this is not the case. So actually, because estimating which point has a higher probability mass can become arbitrarily difficult as they become more similar, as soon as you're with unlabeled data on a budget, you don't get improved rates. The conclusion here is do your minimax analysis until the end, even though you may believe that you get improvements through unlabeled data. As soon as you put it on a budget, this may not actually be the case in a minimax setting. Now, I may have just convinced you that, that our definition is useless because nothing ever changes in this setting. However, in our paper, we do show that there exist problems with supervised rates 1 over square root of L and faster semi-supervised rates, for example, 1 over L or even exponentially fast. Okay, to recap, we provide a definition of realistic rate improvements using unlabeled data. We show how this definition differs from idealistic definitions. I've given one in this talk. We contrast with other definitions in our paper. And you now have a party trick for when unlabeled data doesn't help. Thanks for listening.